we present inversion by direct iteration, an alternative to denoising diffusion for image restoration. Image restoration is a process of generating a new high-quality image from a low-quality observation such that the generated image is compatible with the low-quality input. Examples of image restoration include image denoising, compression artifact removal, super resolution, or motion deblurring. Image restoration is also closely related to image generation. For example, we can imagine being given an extremely degraded image, such as one that is heavily noisy, blurred, or compressed, and asked to generate a new image starting from this low-quality observation. The standard modern solution to image restoration is to train a regression neural network using thousands of pair examples, low-quality, high-quality images. The regression loss penalizes the mismatch between the network prediction and the high-resolution reference target. The main issue is that image restoration is in general an ill-posed inverse problem, which means there are actually infinite different high-quality images that could have led to the very same low-quality observation. If we train a model to directly minimize the reconstruction pixel error, in the best scenario, we will get a model that perfectly predicts the average of all plausible reconstructions. This image will look blurry, since it's the average of many high-quality images. This effect is known as regression to the mean. We introduce InDI, an iterative procedure for doing image restoration and generation. InDI can be seen as an implicit reverse diffusion process that can be applied to any restoration task where we're given paired data for training the model. The key idea in InDI is to split the restoration process into multiple smaller ones. This is done by defining intermediate degradations, here represented by xt, that are convex combination of the low-quality input y and high-quality target x. xt spans from t equals 1, the low-quality input, to t equals 0, given the clean, sharp target image. So instead of directly trying to do one-step reconstruction and go from x1 to x0, what we do is we move little by little through these intermediate steps. The key intuition is that each of these smaller problems will be less ill-posed, so we will less suffer from this regression to the mean effect. To do this multi-step restoration, we need an iterative procedure. This is given by the following proposition, which is a straightforward consequence of our linear convex model. This proposition relates the MMSE estimate of xs, that is, the clean image having degradation at time s, starting from xt, the image with degradation t, where s is smaller than t. Specifically, the proposition says that if we want to estimate the image x with intermediate degradation at time s, given that we know xt, we can actually get it by estimating the clean image x0 and then by doing a convex combination with the current degraded image xt. This means that we can actually recover a slightly less degraded image, let's say at time t minus delta, by estimating the clean image at time t and then doing this very specific convex combination with the current estimate. This proposition gives a way of propagating the MMSE estimate. We can convert this in an iterative procedure, where we start from the low-quality observation y, and then estimate a slightly less degraded image by applying this recurrence. We do this till we reach times t equals 0. Of course, to apply this formula, we require to know how to compute the MMSE estimate of the clean image at any xt. In practice, in a typical problem, we don't know how to do this, but what we can do is approximate this MMSE estimate or posterior mean using a neural network. This network that can be easily trained, since it only requires to record the clean image given the intermediate degradation and the time t. To fix ideas, let us introduce a toy example. Imagine we have 2D noisy points coming from a multimodal distribution, here represented by the 4 orange dots. The noise is assumed to be Gaussian of a known standard deviation. The idea is then to recover the clean samples. In these examples, we know all the components perfectly, so we can compute the exact posterior mean needed for the InDI iteration. If we directly try to minimize the reconstruction error, the best we can do is the posterior mean, which leads to the red dot estimation. As you can see, the red dots are kind of out of the data manifold. This is a visualization of the regression to the mean. However, if we apply the InDI procedure, we end up conversion to a valid point in the dataset. InDI trajectories are the ones shown in green here. Of course, this is a toy example where we perfectly know all the pieces. Let's see a real example in image super resolution, 4x super resolution. Here you can see the difference that you get when applying InDI with different number of reconstruction steps. If we do one step, we go back to the original regression estimation, which is blurry. As we use more steps in InDI's reconstruction, we get images with much more detail. Another example now for removing motion blur using the standard GoPro motion deblurring dataset. On the left, you can observe results when applying InDI with different number of steps. The plot on the right shows that as we do reconstructions with more steps, the FID score, which is a metric more correlated with perceptual quality, gets smaller. There is a trade-off between the average distortion, here represented by PSNR, and the FID score, which correlates with perceptual quality. This is a well-known perception distortion trade-off. With InDI, we can actually traverse this trade-off by controlling the number of steps we use in the reconstruction. Let's dig a little deeper on the technical details. This is InDI iteration. Given that we have an estimate at time t, then we need to compute the MMSE estimate of the clean image from xt, and then do this convex average to get the updated estimate. For the iteration to be well defined, we require to be able to compute the MMSE estimate given our current xt. This implies that no matter what our current estimate is, we should have non-zero probability density function. This is saying that no matter where we are, we will be able to estimate the clean image. One simple way of guaranteeing this is by adding very little noise to the input y. Then all the probability density functions will be supported in the whole space. This is a standard trick for regularizing distributions. So, in the end, our intermediate degradations, xt, are given by this simple convex combination between the input with very little noise added and the clean target. The strength of the added noise is controlled by epsilon. As we will see, this is actually quite important in some applications that we have non-stochastic degradations such as super resolution or JPEG compression. The core block of InDI is a neural network that predicts the clean image given an intermediate degradation. We just use a standard LP loss to minimize the pixel reconstruction error. What we learn in practice is a family of continuous regressors, here represented by f theta, each of them specialized in estimating the clean image given xt and the parameter t. Please check our papers for more details. Once we train the model, doing inference is straightforward. We start by adding some noise to the input and then just iterate in the updates rule till we reach time 0. Let's see an example for super resolution and the role of noise. Here you can see the same distortion perception plot as we showed before. Each of the dots represent the results of applying InDI with a different number of steps in the reconstruction. If we train a model without adding noise, here represented in the blue curve, then no matter how many steps we do in the reconstruction, we get similar results as the one we get when doing a single-step reconstruction. And this is actually the case when when the degradation is deterministic. As we add very little noise, for example, here in the orange curve, where the noise is 0.005, compared to an image that is normalized to be into -1 and 1, then we start to getting results with much better FID scores. Please check our paper for more details. So let's see some other examples. Here you can see in the results for a model trained for doing 4x super resolution. Another example, this is for a model trained to do JPEG compression artifact removal. As we use more steps in the reconstruction, the generated image has much more details. Another example for motion deblurring, and one more for a model trained for doing out-of-focus deblurring. As we mentioned earlier, image generation can be seen as a particular instance of extreme image restoration. Imagine, for example, that the noise in the image is so high that it masks completely the signal. Instead of having an extremely corrupted observation, what we can do is just pair a high-quality image from our trained dataset with an independent noise realization and proceed as before. The goal is then to reconstruct a clean image from the input here represented by Y. If we do this, then we get very interesting results. You can see a few uncorrected examples generated by applying InDI on Celeb A 64x64. The framework is exactly the same as the one we presented for image restoration. The only difference is that here we just pair noise with a high-quality image. Results are not state-of-the-art, but are kind of cool since we didn't tune anything for this generative task. If we look carefully, the InDI framework, when applying this particular case, becomes very similar to a denoising diffusion model. The main difference is that here we are not using any analytical degradation. The degradation is implicitly encoded in Y and X. DDPMs, or denoising diffusion models, are trained to generate images by removing noise little by little. Denoising diffusion models can be adapted to solve image restoration tasks by casting the restoration problem as one of conditional generation. In a conditional DDPM, the model learns to transform noise into a high-quality image conditioned on the low-quality input. Our framework, InDI, directly transforms the low-quality input into a high-quality image. The same framework can be applied to image restoration or generation by changing the starting point. Here you can see a comparison between InDI and a vanilla conditional diffusion model for JPEG compression artifact removal. Both models have very similar architecture, so they have approximately the same capacity in this experiment. InDI manages to get into a similar quality point in much fewer iterations than a vanilla diffusion, since we operate directly on the input image. We can take InDI update rule to a limit and let delta, the step, be very small, close to 0. This leads to a continuous InDI formulation through an ODE. The ODE is quite simple. It's sort of a weighted residual flow where we evolve the image in the direction of the residual given by f, or in the ideal case, the posterior mean. This is useful for exploring other solvers and also for doing more analysis. InDI is very related to our very recent work that explore ideas on score matching, the probabilistic flow ODE, Schrödinger bridge, and optimal transport. Please check our paper for more information. In the particular case where the degradation is Gaussian additive noise, InDI's ODE boils down to a score matching probabilistic flow ODE. Actually, when f in our model is the MMC estimate, The denoising score matching approximation is exact and the relation is given by the Twist formula. We presented InDI, a powerful but simple method to mitigate the regression to the mean effect by moving in small steps. InDI relates to current denoising diffusion models, but the diffusion process is implicit. There's no analytical degradation. We're just given paired data, low quality and high quality inputs. The results are state-of-the-art or competitive in many restoration tasks, and the same framework without any change can be used as a generative framework. Please check our paper for more information. Thanks for listening.